Okay, so this is the second analysis step in which we're making a Michaelis-Menten curve and identifying the Vmax. All right, so to do that, we need to get to our calculation sheet here and go to one of these plots that we have data for. So this one's not too bad here. This is hemoglobin 45. All right, so I highlight the concentration of hydrogen peroxide and the rate data. I copy it like that, and I go into Kaleidograph here and I paste that right here. Okay, so that data there is now in this sheet, and then with this table, this window highlighted or clicked, I go to Gallery, I go to Linear, and then I go to Scatter. All right, the x-axis is the stuff, the concentration in column A. The y-axis is the rate in column B, and I say New Plot, and this one should populate, and it should look just like the one that we were just looking at, right? So this, and I can double check on the x-axis here, goes from 0 to about 1 point something, 9 times 10 to the minus 8 over here. So that's what we should be seeing over in this space. Yep, right? 8 times 10 to the minus 8, 10 times 10 to the minus 8, or 1 times 10 to the minus 7, right? So this is it. Okay? So then I go into, I click on this window, make sure it's clicked on Curve Fit, General Fit 1. All right? And then I go into Define. Now right now the equation that they have here is B plus Y, no, B plus, so this is Y equals mx plus B. So this is the M times the X plus the B. That's a linear fit. But we don't want a linear fit. We want a saturation curve, or the Michaelis-Menten curve fit. And now the equation, and see how it's kind of written in a little bit of an interesting way, where M1 is one of the variables, M2 is a second variable. So that's like M1 is our Y value and M2 is our X value in this case, right? But we want to get the Michaelis-Menten curve. So I have the Michaelis-Menten curve equation in the calc sheet, right? See where we're at? So I can click here, and then I can copy that data there, Control C, that information, that equation, and then I can go into Kaleidograph there. That's not right. Let's see what happened. I think I got rid of it all. Let's try that again. Why did that work? Control C. Control V. So that time it worked. I guess the last time I didn't copy it well. So this is the Michaelis-Menten curve, or Michaelis-Menten equation. If we search the Michaelis-Menten equation, just to see what it looks like. Michaelis-Menten equation, the rate, velocity, is equal to the Vmax, the maximum velocity, or where it asymptotically approaches, times the substrate concentration over the Michaelis constant for the enzyme plus the substrate concentration. So let's see if we can kind of see that in this information here. So here's our substrate concentration is the M1, M0 is the Vmax, M2 is the Km, and M0 is the substrate concentration again. I don't know if you can see that.
Barely.
Okay. But by looking up the Michaelis-Menten equation, I see that it's the Vmax times the substrate concentration. So I look back here. This is M0 times M1, right? I can't zoom in on this old software, right? So one of these, M0, represents the Vmax, and the other one represents the substrate concentration. And then M2 plus M0 on the bottom, so it looks like M0 must be the substrate concentration. So M2 is the Km, and Vmax is the what? M1. MO is the substrate concentration because it's in both sides. See how we did that? That's a little bit important because you need to be able to, I mean, it's almost always going to be the same, but, and we'll actually, probably a good idea to change it.
I was going to say, can I take a picture of that?
What?
Just that, I guess you have it on there.
It's in there, so you don't have to think about it. But what we need to do is we need to give the computer a good estimate for the M1 and the M2. All right. So the M1 was the, what did we say?
Was it the Vmax?
Yes, the Vmax.
Which is where it approaches.
That's right. So right now it's saying that M1 is about 3,500. That's what this equation says here. But it's not, right? This isn't approaching 3,500.
Right.
It's approaching like 1 times 10 to the minus 7 or something like that, right? So I'm going to change that value to 0.1234561. All right? That's what this Vmax looks like it's approaching. The other variable, M2, is the Km. The Km, or the Michaelis constant. And that is the concentration of the enzyme necessary to get half the Vmax rate. So we decided that this is the Vmax rate, right? Half of that is 5 times 10 to the minus 8. See that? So here's the Vmax, half the Vmax. And if I look and see what concentration gives me half the Vmax, I see that it's right about here. If I imagine a slope, a line going through there like that, right? So I say about halfway here, I come over here and say this is where it would kind of intercept with the line. And you don't need to be precise. It's going to adjust and find it. But then this down here, which is about 0.025 maybe, needs to go in here for this 500. 0.025. All right? And then I say, and I'm going to actually copy this. And we'll paste this as this is a better starting point for our Michaelis-Menten equation there, yeah. All right, so that'll be a lot easier because that'll almost fit all the data that we have right now. Back to here, we say OK. Click on that box, showing that column B is what we're going to be analyzing here, and then we say OK. And then it fits it for us using that equation, okay? And then the Vmax is what we're after. Do you remember which one was the Vmax?
M1.
Yeah, M1. And that's consistent with that. See, 8.4 times 10 to the minus 8. Okay? So that 8.427 times 10 to the minus 8, that's the Vmax now for, let's go back to our data here, for this one, right? Is this the one we just did, or which one?
I'm not sure which one.
Well, that's no good.
I can remember what the graph looks like, kind of.
Was it this one?
That one. Oh, we did say.
It looks like this, right? 1, 2, 3. So I think this is it, right?
Most likely. We don't know. You said it in the beginning of the video, I think, which one it was.
I'm pretty sure because this is, well, here's how we can see for sure. 8.33 times 10 to the minus 8. 8.33 times 10 to the minus 8, right? Okay, so this is it. All right, so 8.4278 times 10 to the minus 8. 8.4278 times 10 to the minus 8. I'm going to put that in here for this Vmax. Okay, so I put in the 84278, and this is times 10 to the minus 8. And when I present it should say 8.4 something times 10 to the minus 8.
Beautiful.
Okay? Now, this is an older set. The newer sets that we have this extra little component in there. See that? I'm going to bring this over to this older set here. This is it right here, right? I'm going to paste that right there. Okay. The Vmax, this sheet converts or identifies the KCAT from the Vmax. Okay? And the way it does that is it takes the Vmax, like this equation says, and divides it by the enzyme's molar concentration. If you ever make a mistake like that, you can always push escape and just get out, or you can push undo after you do something. So this KCAT, we double click on here and make sure that this is on the hemoglobin concentration. And we know to put it on the hemoglobin because it says hemo right here. It was already had the hemoglobin concentration up here. But the problem was we were collecting data for myoglobin sometimes, and it had the hemoglobin concentration because we would just copy and paste and wouldn't change that concentration. This is the concentration when we run myoglobin, right? So now I can double click here to verify. It takes the Vmax, divides it by the hemoglobin concentration, and that's it. And then this one here just takes the natural log of that one there.
Perfect.
Okay? So now this is the natural log, 2.79, natural log of our KCAT. That's our final number, 2.79. This is at 45 degrees Celsius, hemoglobin 5. So I can go over here and say if this is our Hem 5, 45 degrees Celsius. What was it?
No, it doesn't matter. For this program, it doesn't
2.79 times 10 to the 0, so it's just 2.79. Okay, so this is actually looks like the natural log of the rate, little k. 2.79. Okay, so this is plotting the natural log of k versus the temperature. Now 45 is in Celsius. We need to add 273 to that. What is that? 273.15. Is that right?
318.
318?
It was 45.
Yeah, 45.
Yeah, 318.
Okay. All right. So that's the second step.
Okay. Is there a third step?
Mm-hmm.
Are you sure?
What?
I said, are you sure?
Yeah, I'm sure. Okay, so that's that. I think that video is enough, and you should be able to go through it and do it again following that video, right?